The next speaker is Hayden Lee. He will continue to teach the cosmological bootstrap today.
Thank you. So, all right, so let's pick up from where we left off last time. So yesterday we started looking at the formalism using the wave function of the universe to compute cosmological correlators. And we looked at the simple toy model, just a massive scalar field in flat space. And we learned how to compute tree-level endpoint wave function coefficients in this simple toy model. And this is the exercise that I left you to do. So the calculation of this simple tree-level 4-point wave function coefficient, you can compute this using the Feynman rules involving two sets of set of two propagators. So the bulk-to-bulk propagator denoted by K, and the bulk-to-boundary propagator denoted by K, and the bulk-to-bulk propagator denoted by G. Okay, and then you would do the number of time integrals corresponding to the number of interaction vertices, and because the bulk-to-bulk propagator contains three different terms, you would compute this object using the time integrals by doing these three time integrals separately and then combining this way. Okay, so those expressions are the result for the individual time integrals. And then you would sum over them with a relative minus sign for this boundary term. Okay, and you see that when you do this, you try to combine all of the terms in the common denominator. You get 4 factors downstairs. So notice that every term above contains this factor of 1 over Ki, where Ki is the intermediate momentum. But when you combine all of them, it turns out that there's some cancellations. Okay, so K12 cancels, K34 cancels. So in the numerator, you get twice Ki, which actually cancels with the Ki in the denominator. Okay, so in the end, you get a much simpler answer, which is given by this expression in terms of the energy variables that I defined. Okay, 1 over E times E left times ER, where E denotes for the total energy. So that is the energy associated with the whole graph, Feynman graph. E left is the energy associated with the left vertex, and E right is the energy associated with the right vertex. Okay, so we get this relatively simple looking expression when you look at the final result. Okay. And then we looked at some properties of this wave function, noting that there is this interesting energy singularities, right? So I mentioned that there's this interesting property that if you take a general endpoint wave function coefficient, then there's a singularity that goes as 1 over E, and the coefficient of this singularity is given by the corresponding amplitude in flat space. So this is a relation that I mentioned briefly towards the end of the last lecture. So that was the singularity at E equals 0. Now, there are also other singularities at E left equals 0 and E right equals 0. So we also want to know what happens, for example, when we set E left to 0. Okay. Any guess of what should happen when you take this limit? So the physics behind this E total singularity is that you're basically taking all of this interaction all the way to the path infinity, right? That's why you reproduce this flat space object. Now, what happens when you take E left to 0? You're basically dragging this energy associated with this vertex and the time integral associated with this vertex all the way to minus infinity. Okay. So what do you think would happen in that case? Yes? That's right, yeah. So the answer is that what happens is that because you're dragging this vertex all the way to the path infinity, you get an amplitude associated with this vertex. So you get an interesting factorization behavior. So if you take the wave function coefficient and then take, say, E left to 0, you get this singularity as E left equals to 0, 1 over E left, times the amplitude associated with the left vertex, multiplied by the wave function associated with the right vertex, with some modification. Okay, so it's not exactly the wave function associated with the right vertex, but some related object. And to see what this object is, we can look at the behavior of the green function. Okay, so going back to time integral representation. Now, in this limit, you're basically taking the left time associated with the left vertex all the way to the past infinity. Okay, so this limit in the time integral representation is equivalent to taking the left time all the way to minus infinity. And what happens is that when you look at the expression for the bulk-to-bulk propagator, now the first term doesn't survive when you take the limit because t is much less than t prime. So a theta function kills the first term, whereas the second term survives. So theta function becomes 1. So you get a combination of the second term and the third term, okay, with a relative minus sign. So what happens is that you get this behavior. So you get 1 over twice k times e to the I k t. So the second term and the third term has a common factor of e to the I k t multiplied by the difference between e to the minus I k t prime minus e to the I k t prime. Right? Okay. So that means that when you take this limit inside the time integral, what you will get is that this time integral over t will reproduce the amplitude on the left side. On the right side, you will get some combination of the wave function where one of them will have a flip sign of the k. Okay? And notice that this Green's function is associated with the internal energy. Okay? So what will happen is that this, so what I'm defining as psi tilde here, will be given by 1 over twice internal k, multiplied by the wave function you would get by flipping the sign of the internal energy minus the wave function. Okay? This behavior follows from the behavior of the Green function. And this is the final factorization behavior you get. Yeah? Yeah, so this is the argument that I briefly gave last time. So if you have an integral from minus infinity to 0, e to the I kt with some other stuff. Now, let me write it e left. Okay? If you take e left to 0, then this integral blows up because this oscillating factor, which usually suppresses the contribution from minus infinity, actually becomes 1, so it doesn't suppress this singularity anymore. So all the integral is dominated by the contribution coming from minus infinity, so it doesn't really care about the cutoff. Okay, it doesn't really matter whether there's a finite t or, yeah. Okay. Okay, so we get these interesting singularities appearing for the wave function, and we now understand the behavior of these singular limits for the wave function. Now, these properties can be also checked for the higher point functions. For example, the next complicated case, next non-trivial case would be this graph, okay, which will secretly correspond to some 5-point function. Now, if you want to do this using the time integral method, you would do a triple time integral with 2 bulk-to-bulk propagators. And each bulk-to-bulk propagator has 3 terms. So in total, this can be computed by summing over 9 different terms with all the various time orderings. Now, it turns out that if you sum over all of the terms, you get the following answer. So notice that the final answer you get is actually much simpler than what you would expect by doing this naive time integral calculations. And notice that if you were to do this time integral calculation, then each bulk-to-bulk propagator will also have some singularity. So each bulk-to-bulk propagator will have things like k internal prime, right? But when you sum over all of them, these will cancel with some dependence of this case on the numerator. So in the end, the final result will just depend on the energies. So here, these are various variables I'm referring to as, for example, this E is the total energy, just like the previous case, the energy associated with the whole graph. And this E1 would be the energy associated with just the first vertex. And E12 would be the energy associated with the first 2 vertices, okay? But there's no single dependence on these internal energies in the denominator, okay? So on observation is that these wave function coefficients have these interesting energy singularities, and only those. There's no other singularity. So the only possible singularities for these tree-level wave function coefficients are these energies, total energy and the partial energy associated with these subgraphs. Okay. All right. So you see that the final results for the wave function tend to be much simpler than this time integral representation. So the question you should be asking is how can we make this simplicity manifest? Okay. Is there a way of making this simplicity for the final wave function manifest without considering this time integral representation? And it turns out that this philosophy is going to be very helpful when we look at the actual cosmological correlation functions, because things will be start to become quite complicated when you go to an actual cosmological spacetime like de Sitter, which is relevant for inflationary calculations. Okay, so let me describe why this is the case. So let's now go to de Sitter space. So instead of having the Minkowski metric, now let's consider de Sitter metric, where here eta is conformal time and a is the scale factor in de Sitter, which goes as minus 1 over h eta. Okay. So now eta stands for the time variable. Okay. So yesterday I mentioned how to compute the wave function coefficient by evaluating the classical action. Okay. And to obtain the classical action, you solve the classical equation motion. Okay. So yesterday we solved this equation for mass-free scalar field, but now we are in de Sitter, and this time we'll have the box operator in de Sitter, and let's also add a mass. So this will be the equation of motion for scalar field in de Sitter. Okay, so let's solve this in Fourier space. Okay, so we can go to Fourier space. So this now becomes an ordinary differential equation in eta, the time variable. So let me write it. Okay. So this is the equation of motion in Fourier space. And we can solve this equation. So the solution is given by a Bessel function or Hankel function, which is a type of a Bessel function. So phi, if you plug into Mathematica, it will give you a solution that looks like this. 3/2 minus delta minus k eta. So this is a Hankel function of one of the two Hankel functions, Hankel 1 and Hankel 2. And this is some combination of Bessel functions. And this delta is the scaling dimension of phi, which is defined to be 3/2 minus square root of 9/4 minus m squared over h squared. And this is a scaling dimension since this solution will go as eta to some power delta as eta goes to 0 towards the boundary of this order, future boundary of this order. Okay. All right. So this is the classical solution. So now we can play the same game of defining the corresponding propagators. Now, the bulk to boundary propagator will be given by this Hankel function. Bulk to bulk propagator will be given by a product of these two Hankel functions with the theta functions. Okay. So in the end, we are interested in computing correlators in this order that looks like this, where the external legs will be some massless scalar field, like that plays the role of the inflaton, okay, nearly massless scalar field. And in order to probe some new physics during inflation, we can consider some coupling between the inflaton and some extra heavy field. Now, you can evaluate this wave function by writing down this time integral. K12, G, K internal, K3, K4, right? With different forms of these propagators. Now, these external, both the boundary propagators, if the scalar field is nearly massless, is going to be pretty simple. So the above solution, in terms of the Hankel, is actually becomes quite simple for massless scalar field. So it becomes this simple modified plane wave for massless scalar field, or if you plug this m equals 0 above, it gives the scaling dimension of 0. Okay. There's also other simple case where if you set m to be square root times Hubble with delta equals 1. Okay, so if delta is an integer, then you also get this rather simple behavior. So this is massless case, and the other case is when the scalar field is a conformally coupled scalar. Okay, so this simplifies the bulk-to-boundary propagators, but the bulk-to-bulk propagator will contain, for generic masses, will contain this product of two Hankel functions. And this sort of integrals with two Hankel functions with time ordering is not something that, for example, Mathematica will do it for you. So unfortunately, you can't just rely on Mathematica. Or you can't really find these integrals, for example, in Greshstein and Reisig either. So what do you do? So we'll try to stick to this philosophy. Okay. So instead of working directly with the time integrals, we want to see whether we can directly fix the wave function that lives on the future boundary using some other means. Okay. So that's basically going to be the driving philosophy in this lecture. Okay, so let me now talk about a method called cosmological bootstrap. Okay, so the idea is to try to determine final boundary observables without time. Okay. So in order to do this, what we'll do is to use a set of physical constraints that these objects must satisfy. For example, there could be some symmetry constraints, locality constraints, unitarity constraints, and so on. Okay, we want to combine all of these constraints and then and working directly in kinematic space where these boundary correlators actually live, and we will try to see whether these constraints are sufficient in order to fully fix the answer. Okay. So since most of you are working on amplitudes, let me quickly mention how these are used to determine the simple full particle amplitude in flat space. So for amplitudes, if you have a full particle, the 2-to-2 scattering amplitude at tree level. Okay, so this is the analogous flat space object that we are interested in. So in this case, there's first of all symmetry constraints from Lorentz invariance. Okay, so this tells you that amplitude is a function only of the two Mendelssohn variables S and T, right? And there's a constraint from locality, which implies that amplitude should have a simple pole when the particle goes on shell, right? Okay. Now the question is, so this is, for example, enough to fully determine the structure of this simple scalar 2-to-2 scattering amplitude. Of course, if you have unitarity, then also demands consistent factorization when you go to this pole. Now, the question is, what about de Sitter and inflation? Okay, what are the corresponding constraints when you go to de Sitter or near de Sitter that describe inflation? Any questions so far? The philosophy clear? Yeah? Okay. All right, so let's begin by looking at symmetry constraints. And we will work in exact de Sitter for now, and then I'll explain towards the end how to go from the de Sitter answer to an actual inflationary correlator that we care about. Okay, so we are interested in computing this boundary correlator. Okay. That lives on the future boundary of de Sitter. So this surface is just a spatial surface, R3. And in the bulk, there's some process that generates this correlator that happens in de Sitter 4. Okay, so 4-dimensional de Sitter space. Now, de Sitter has a large symmetry group, the large isometry group, called SO4,1. Okay. So this is equal to a de Sitter isometry group when you consider the isometry group in 4 dimension. Okay. So D equals 4 is equal to the de Sitter isometry group. But when you go to this late-time surface, just a spatial surface, which is a 3 Euclidean space, this symmetry group can be identified as the conformal group in D equals 3. Okay. It's SO4,1, yeah. So in general, the spatial dimension is going to be D plus 1, 1. Okay, and so we can identify this as the conformal group in the boundary Euclidean 3-dimensional Euclidean space. So we can try to impose. What we can do is to try to impose this conformal symmetry constraint on this boundary correlator. But if you notice, this is actually the familiar Lorentz group. When you think about this isometry group as acting on some object in 5 dimensions. Okay. So of course, in D equals 4, SO3,1 is the usual Lorentz group. Okay, and the Lorentz symmetry is actually quite easy to impose compared to the other symmetries. Okay, so in order to really efficiently impose the symmetry, it is actually helpful to first consider de Sitter in 5 dimension, and this can be done by thinking of de Sitter as some hyperboloid living in a higher dimension. Okay, so de Sitter 4 can be thought of as some hyperboloid living in one higher dimension. So you have this dot product being equal to 1 over h squared, where h squared describes the de Sitter radius, this radius of this hyperboloid. And the reason why it's useful to first consider de Sitter in this so-called embedding space is that symmetries act very nicely on this object because it's just the Lorentz symmetry acting on this. So let's go to right. So the symmetry generators are just Lorentz generators, which take this usual form given by this. So here, this capital X is the embedding space coordinate. And okay. All right, so we have the symmetry generators that act on this global de Sitter space. But now we want to understand also how the symmetries actually act on the wave function coefficient that we want to compute. Okay, so how do these act on these wave function coefficients, psi n? So that's the next question. So let's go back to the definition of this wave function coefficients. Okay, so these wave function coefficients appear as the when you expand the wave function psi, which is a function of this boundary profile phi. It was given by taking e to the I action, classical action, Okay, so you get e to the some terms here, and then if you look at the nth term in the expansion, then you had this integral. Right, you had some perturbative expansion in this exponent, and if you look at the nth term in this expansion, that gives this psi n. It has this integral structure. Now, first, you can what you can do is to look at the scaling dimension. What is the scaling dimension of this object? So, so here I mentioned that this bulk field in the sitter has some particular scaling dimension delta at late times. Okay. Let me denote it by delta phi for the scaling dimension of this scalar field. Now, this whole integral has to be dimensionless. Okay. So that means that because these major factors have dimensions, that implies that dimension of this wave function must be 3 minus delta, where wave function can be thought of as being some correlator with some n operators. So by 3 minus delta, I mean that this operator, individual operator, have this dimension 3 minus delta phi. Okay. So if the individual operator has this dimension, then the whole integral is dimensionless. Okay. It's just a notation for just a generic operator. You can call it something else like phi tilde. Yeah. I'm using the notation O because this wave function you can think of as having the exactly same constraint as being a correlator in a CFT. Okay? In CFT, you talk about correlators operators. Okay, so yeah, so psi n, it turns out that it transforms as a correlator in the d-dimensional conformal field theory that is conformally invariant. Oh, yeah. With dimension of the operator given by this. And it satisfies this constraint. Okay. So these were the symmetry generators. So the correlator must be annihilated by the action of these symmetry generators. Okay, so you can think of this as being the conformal word identity. Okay, so if you act with this conformal symmetry on the function and the sum of all the actions on the individual operator, it has to be 0. Okay. Now we can try to massage this equation a little bit because this equation is still in defining embedding space because it has these embedding space indices. But we want to compute this object ultimately in momentum space, right? So what you can do is to project these embedding space operators onto this 3-dimensional slice in position space, and then you do the Fourier transform. But to do that, you first want to get rid of these indices. So what you can do is to either, so let's consider 4-point function. Okay, so you would have, let me write it in this way. So I just collected M1 and M2 and M3 and M4 together. Okay, so this is the conformal constraint on the 4-point function. What you can do is to contract this equation either with M1 plus M2 or with M3 plus M4. Okay, and then take the difference. Okay, and what you get then is the following equation. Okay, when you take the difference, the cross term cancels out, and this is the equation you get. So here you're taking the dot products to sum of all the indices. Now you can project onto the lower three-dimensional slice, okay? And then you do the Fourier transform. And this Lorentz generator squared, you can identify as the Casimir operator for the isometry group. Okay, so let me call it C12 and C34 for Casimir. Okay, and this is really the analog of this constraint for amplitude. So you have S12 minus S34 amplitude. Okay, so 4-point amplitude has a momentum conservation, and therefore S12, the Mandelstam, defined by squaring P1 plus P2, is equal to P3 plus P4 squared. Okay, and this is obviously satisfied for amplitude, and you can think of this differential equation as being the analog of this condition for correlator. Okay. So let's try to solve this equation. That's the plan for the remaining lecture. Okay, so let's try to solve that differential equation for the simplest possible case first to get some idea. Okay, and the simplest possible case. The question. Instead of conformally coupled scalar. With dimension of the scalar field equals 1, as I wrote down before, which implies that dimension of the corresponding operator for the wave function is 2. Okay. All right. So first of all, some kinematics. Okay. So because we have a 4-point function in momentum space, the spatial momentum momenta sum up to 0 by spatial momentum conservation. Okay. So we have K1, K2, K3, K4. And then we also have internal momentum, which I'll call Ki. Okay, so we have 4 momentum, spatial momentum, 4 spatial momenta. So the total number of degrees of freedom we have that describe this 4-point function is 3 times 4 to begin with. But there's a whole set of symmetry constraints that this 4-point function needs to satisfy. And the Lorentz group, or the conformal group in 3 dimensions, okay, so generically, the number of constraints coming from symmetry for d spatial dimension is given by this. So this is just the dimension of the Lorentz group. For d equals 3, this is equal to 10. So the actual degrees of freedom that describe the 4-point function is just 2. Okay, so there are 2 independent variables that characterize the shape dependence of the 4-point function. Okay, so we will define some 2 dimensionless variables to work with. Okay, let me call it U and V. where U is defined to be the ratio of the internal momentum and the sum of the two side lengths, K1 and K2, and V is the permutation of U, so ratio of Ki over K3 plus K4. Okay, so that's just definition. All right, so first constraint we can solve is actually the scaling constraint due to scaling dimension. Okay, so when we have this correlator, 4-point correlator in position space, I told you that individual operators have dimension delta O. Okay, so this has dimension 4 times delta O, right? But we want to work in Fourier space. Okay, so we want to compute this object instead. Okay, with K1 to K4. Now, what's the scaling dimension of this corresponding Fourier space correlator? Well, it's 4 times delta minus, you have to, when you Fourier transform this object, the measure factors, okay, each of which has dimension 3. Okay, so you have to subtract 4 times, say, little d for the spatial dimension. But also recall that the 4-point correlator in Fourier space has a momentum conserving delta function, and delta function has a dimension d as well. So we have to compensate for this. So this comes from the Fourier space integral, and this comes from delta function for momentum conservation. Okay, so this dimension was 2 for conformally coupled scalar, and this so 4d plus d is minus 3d, and d is 3. So scaling dimension is minus 1. Okay. So let me call this object psi. So psi has overall scaling dimension of minus 1. So we can trivially solve this constraint by just defining psi hat by factoring out this 1 over ki. And this psi hat is going to be some dimensionless function of dimension variable u and v. Okay. Any question about that? Okay. Well, that was the most trivial constraint. But what we want to do now is to solve this constraint, the full conformal constraint. Okay. All right. So we want to represent this C12, the Casimir operator, in terms of the momentum variables, in particular, in terms of these U and V variables. This is an exercise you can do. And let me write down the answer. So it's going to be some second order differential equation operator in U. When you plug in delta equals 2, C12 takes this form, some second order operator in U, and C34 is the same operator in V. Okay. So let me define this as some differential operator in U, D sub U. So the conformal constraint for the correlator that we want to solve is now this. Okay. So this is the conformal invariance constraint. That we want to solve now. notice that this is just a purely kinematic constraint. So far we haven't specified any dynamical information. Okay, so this constraint is just a purely constraint due to symmetry that has to be obeyed by any correlator arising from any dynamical process. But solving for this constraint is too general. Okay, so what we want to do now is to specify some dynamical information, and we want to solve this object for some very simple dynamical processes like tree-level contact interactions, exchange, diagrams, and so on. Okay, so what we need to do is to provide some information about what this solution has to satisfy. In particular, we can specify the information about the singularity. Okay, so singular behavior of this wave function, because from the flat space calculation, we observed that the only possible singularities that this wave function can have at tree level are these energy singularities. Okay, so we want to make some ansatz of the singular behavior of this psi, and then plug into this equation and see what we get. Okay, so that's what we can do. Okay, so let's try to do that for simple tree-level processes. So we will start with contact interactions, like 5 to the 4th. Okay, so we are imagining that we will be computing the wave function coming from this sort of interaction. Okay, and this sort of contact interaction, the only possible energy singularity is the one associated with the total energy. Okay, so there's just single vertex. Okay, so this should have some sort of 1/e singularity and nothing else. Okay, right. So this psi now it must have this 1/e singularity, but what else it needs to satisfy is this. Is that it has to be consistent with this scaling dimension. Okay, if we are solving for the 4-point function with the conformally coupled scalar. Now it turns out that this 1/e, this simple function, already has a scaling dimension of -1. Okay, so our natural guess is whether this psi is just simply given by 1/e. And if we want to check this, we first have to convert this expression 1/e in terms of the u and v variable, and we can show that this is given by this function. Okay, 1/ki times uv over u plus v, and you can easily check with your Mathematica that this is indeed invariant on the conformal symmetry. Okay? Okay, so this is the solution for 5 to the 4th interaction. What about other contact interaction like higher derivative contact interaction? Turns out that there's a very simple way of generating the corresponding wave function for the higher derivative interactions. If you know this solution, okay, so you know this solution. So let me call this psi contact. Now, if you know this solution, what you can do is to generate different solution by simply acting with this n times. And then you can easily see that this is, again, solution to the conformal invariance equation, because if you act with this du n times, then this du operator obviously commutes with dv, because u and v variables are independent, and also, of course, du commutes with itself. Okay, so that means that this function, this new function we generate by acting multiple times with du, satisfies this conformal invariance equation, because we can just simply pull this du operator outside, right? And these are the solutions to this. And this gives an extremely efficient way of generating all possible wave function with any higher derivative interaction you like from the purely boundary side. Whereas if you really want to do the bulk computation of this object, it's going to be horrendous. You have to care about covariant derivatives for higher derivatives, and doing all of this time integral is going to be super complicated. But this is a very nice boundary way of generating the answer. Now, what about exchange diagrams? Okay, so we want to consider diagrams like this. Okay, so here is phi are assumed to be conformally coupled scalar, but we want to compute this 4-point correlator with some exchange of some arbitrary heavy operator. Okay. Okay. So here, when we looked at this conformal invariance equation, we noticed that these Casimir operators actually play the same role as the Mandelstam variables for amplitude. And this continues to be the case. So if you have a particle exchange for amplitudes, then the mass shell condition is given by this, p squared minus m squared equals 0. Now, in our case, what happens is that if you have some operator exchange that correspond to sigma, then it will satisfy this so-called Casimir equation. Okay, so this is a Casimir. This m hat is the Casimir eigenvalue. Okay? And this, in terms of the dimension of the operator, is given by this for a scalar field. Okay. So let me also write it in terms of the explicit mass of this object. So this is given by 9/4 plus mu squared, where I'm writing delta as 3/2 plus sin e. Okay, so using this, we find that the correlator, exchange correlator, must satisfy the following equation. Okay, so if you act with this operator on the exchange correlator, then what it does is that basically collapses this propagator, after which this 4-point function just becomes this contact diagram. And this is completely analogous to the fact that if you take a exchange amplitude and then just multiply by this inverse propagator, obviously it kills the pole and you're left with simple contact amplitude. Right? Okay, so there's a very nice analogous story that we have in de Sitter, except that this is not an algebraic constraint. So this is a differential equation that you have to solve to obtain the final answer. Okay, so let me write down the equation that we are going to solve. So equation we're going to solve, writing back in terms of the u variable, it's going to be this equation. Okay. So we have this equation on the left-hand side with some second-order differential operator. So this is mu squared. Acting on this exchange wave function gives the contact wave function. And let me also write down the explicit form of this contact wave function given by this 1 over E. Sorry? Sorry, yeah, it should be just C1. Yeah, thank you. All right. So, so before fully solving for this equation, okay, so if actually it's gonna take me, if I want to go through the full derivation, it's gonna take me at least an hour, another lecture to go through. So instead of going through the derivation, let's just try to look at some interesting behavior of this equation, okay? So notice that this equation has several singularities, okay? So for example, if this equation becomes singular when you take u going to 0 limit, okay? Or u going to plus minus 1. Also, there's a singularity when u goes to minus v. Okay? It turns out all of these have a physical interpretation, okay? So there are various singularities at u equals 0, u equals minus v, and u equals plus minus 1. Okay, so let's look at this behavior. So first of all, what happens when we take u to 0? So u variable was defined as the ratio of k internal over k1 plus k2. So this is the limit where you're taking ki much smaller than k1, 2. Okay, so this is like taking this 4-point function where you're collapsing the internal momentum. Okay? So in this limit, what happens is that you can ignore the first term. This term in the first term, and then the rest of the term takes this form. So you get this operator from the second derivative, and you can ignore this and keep the constant term. And this term vanishes when you take u to 0. So you actually get this behavior. So that this behavior implies that this psi exchange has some particular scaling dimension when u is taken to 0. And this behavior is psi exchange goes as u to the power 1/2 plus minus IB. Okay. So you have some oscillating behavior as u is taken to 0. I probably don't have, yeah. Yeah, you can because there's a du squared.
Okay.
Yeah, so u squared or yeah, it scales like constant. Yeah, so basically this extracts the scaling dimension of psi exchange. Yeah, so you can write this as some I don't know, some scaling operator du squared. I think, yeah, if you define du as some scaling operator, it's gonna be like minus something like that. Okay, so I probably won't have time to go through all the behaviors, but let me just mention that when you take u equal to minus v, so this is really e going to 0 limit. So in this case, what happens is that you can show that this behaves as 1 over lambda stem e log e, where this is the corresponding flat space amplitude. Again, it's appearing as the coefficient of the e going to 0 singularity. And finally, if you take u to be plus minus 1, you will get the following behavior. So u exchange will have two types of singularity, where goes as log of 1 plus u and log of 1 minus u. Now, this singular behavior as u goes to minus 1 is precisely the energy singularity that we saw. Okay, so this is the E left going to 0 limit. Okay, so in this limit, you expect the wave function to be factorized in this way. Now, this limit, if you express in terms of momentum, it's the limit where ki is taken to k12. Okay, so this is a limit where you're kind of folding this quadrilateral into this triangle shape. Okay, and this is for that region, it's called folded singularity. But I mentioned before that the only possible singularities that this wave function coefficient can have are this partial energy and total energy singularity. And that is true when you impose the Bunch-Davies initial condition. But if you don't impose Bunch-Davies initial condition, these folded type of singularity can generically arise. Okay? But this is going to be absent in Bunch-Davies. So if you want to fully fix the solution, what you have to do is to impose consistent boundary conditions where you're demanding that the wave function consistently factorize at this partial energy singularity, and then you also demand that there's no folded type of singularity when you look at the full solution. Okay, so the final answer for psi exchange, you can solve the inhomogeneous differential equation. Okay, so inhomogeneous solution plus homogeneous solution. So this, if you solve, it's going to be some sort of a double series solution in U and V. Now, this is not uniquely fixed until you specify the boundary conditions. Okay, and the boundary condition you fix is demanding that you get some consistency. Consistency at U and V equals plus or minus 1. Okay, so that fully fixes the solution. And if you look at the behavior of the final solution, say as a function of U, we saw that U oscillates as U is taken to 0. Okay, so if I rescale it by 1 over square root of U, then you get sort of this sort of behavior where it oscillates, and the period of the oscillation encodes the information about the mass of the particle. Okay, so turns out that imposing consistency on the purely boundary side is enough to uniquely obtain the solution in this case, and you get this behavior that the solution oscillates with a mass dependence. And this is precisely the fingerprint of this having some heavy particle in inflation that oscillates in time, and oscillation in time during inflation gets reflected in this oscillatory behavior of the correlator on the boundary. Okay. Any questions about this? Yeah. Yeah. So if sigma is non-scalar, what you can do? Okay. So far, what we have computed is this object with a scalar sigma. So now, what happens if you add spin? Or now the interaction that we assume implicitly was this phi squared sigma interaction, precisely because when we collapse this propagator, it reduces to 5 to the 4th, which was what we assumed for the source term on the right-hand side. Now, you might be interested in other processes. So ultimately, what you care about. So here, again, this was for conformally coupled scalar field. But ultimately, what you want is the correlator for the inflecton field, which is almost massless. Now, you might be interested in some derivative coupling of this. With some spinning heavy field. And you expect this derivative coupling because a scalar field is nearly massless, so you expect to have some sort of a shift symmetry. Okay, so you want to so what we have so far is this object, and you want to figure out how to go to this object. It turns out that there's some differential operators that you can act on this object that will shift the spins and masses of this field. Okay, so in particular, this object we computed this for delta equals 2. And this object has delta equal 3, and there's a nice differential operator that can shift the dimension of the field by integer units. And these are so-called weight-shifting operators. Sorry? Do they have no? Yeah, so there's a precise some set of operators where here is the sort of the weight shifting operator that shifts the dimension of the external field, and then there's also spin ranging operator that takes the scale exchange to the spin exchange. And these all of these have some known form which you can derive from conformal symmetry.
And you can solve.
Yeah, you can. Yeah, I mean you don't have to solve it because you're just acting with the derivatives. So if you know this one, it's very efficient to generate this final object. Any other questions? Okay. If not, let's come back after the break.